Welcome back to another episode of Second Career Pilot. Today, uh, you know, as a new pilot, it's really important to understand what makes your airplane tick, what powers it. And those fundamental systems, it's not just about passing your exams.
Yeah.
It's about really building confidence and staying safe up there. So we're going to kind of take a personalized look under the hood today, focusing on the engine and propeller, which are really at the heart of every flight.
Yeah,
We'll
absolutely.
explore the different types of engines you might encounter, how they create power, and the absolutely crucial role the propeller plays in getting you airborne.
Exactly. It's easy to look at an airplane as just one complete machine, but it's really a collection of interconnected systems. And the power plant, the engine and propeller working together, that's where the magic begins. At its core, an aircraft engine needs to produce thrust. And for smaller aircraft, like the ones you'll likely be flying early on, reciprocating engines are the most common. And they team up with the propeller to generate that forward motion. Now, it's worth noting that other engine types, like turboprops, they also use propellers, but in that case, the propeller is driven by a turbine, which extracts energy from hot gases. Then you have turbojet and turbofan engines, which create thrust in a very different way, by forcefully expelling a large volume of air. But no matter the type, all aircraft engines also have the vital job of powering the other essential systems on board.
Okay, so let's break down these reciprocating engines. Since that's what most of us starting out will be flying, what's the basic principle of how they actually work?
Well, at its heart, a reciprocating engine transforms chemical energy, that's the fuel, into mechanical energy. This happens through the back and forth or reciprocating motion of pistons inside the engine cylinders. What's really fascinating is how much this technology has evolved over the years, thanks to advancements in materials and design, especially in recent decades. We've seen significant improvements. For example, computerized engine management systems are now integrated, which give you better fuel efficiency, lower emissions, and less work in the cockpit for you managing the engine.
Yeah, those definitely sound like good improvements. Now we have two main types of these reciprocating engines, spark ignition and compression ignition. Can you explain the key differences and how they get that fuel to burn and create power?
Certainly. So the spark ignition engine has been around for many years. It's been used as the standard. In this type, the fuel and air are mixed together before they enter the cylinder. Then a spark plug provides an electrical spark that ignites this pre-mixed combination, causing combustion and generating the power. So the key is that pre-mixed fuel and air needing that electrical spark to get things going.
Got it. So that's the familiar setup. Now, compression ignition sounds a lot different. How does that work?
It is a different approach. Compression ignition engines, often called jet fuel piston engines, don't use a spark plug. Instead, they first compress the air inside the cylinder to a very, very high temperature. This intense squeezing of the air generates so much heat that when fuel, typically diesel or jet fuel, is injected into this superheated air, it ignites automatically. This offers some potential advantages like potentially lower operating costs and the convenience of using readily available jet fuel at airports.
Interesting. So while the way they ignite the fuel is different, are the main mechanical parts inside the engine pretty similar between these two types?
Yes, the core mechanical components are quite alike. Both spark and compression ignition engines use cylinders where the combustion happens, pistons that move up and down within those cylinders, and a crankshaft. The up and down motion of the pistons is converted into the circular motion of the crankshaft, which ultimately turns the propeller. So the real difference lies in how that fuel-air mixture gets ignited.
Okay, that makes sense.
Yeah.
Now, the outline also mentions different ways these reciprocating engines are classified, starting with how the cylinders are arranged. What are the main arrangements a new pilot might encounter?
There are a few common cylinder arrangements you'll see. Radial engines have their cylinders arranged in a circle around the crankcase, almost like the spokes of a wheel. These were quite popular in older aircraft, especially during World War II, because they offered a good amount of power for their weight. Then you have inline engines, where the cylinders are in a straight row. These can have a smaller frontal area, which can help reduce drag, but they tend to have a lower power-to-weight ratio and can have cooling challenges for the cylinders at the back. V-type engines have two rows of cylinders set at an angle, giving them more horsepower than an inline engine, while still keeping a relatively narrow front profile.
And what about the most common type we'll see on smaller training aircraft today?
That would be the horizontally opposed engine. As the name suggests, these have an even number of cylinders positioned on opposite sides of the crankcase, essentially facing each other horizontally. They're usually air-cooled and mounted horizontally, and they're very popular for smaller aircraft because they provide a good power-to-weight ratio. They're compact, and their flat shape helps to minimize drag.
Got it. So radial inline V-type. and horizontally opposed. Good to keep those in mind. The next way to classify them is by their operating cycle, two-stroke versus four-stroke. In simple terms, what's the key difference in how they produce power?
The operating cycle describes the sequence of events that happen inside each cylinder to generate power. In a two-stroke engine, all the necessary steps intake of fuel air compression power production and exhaust of burnt gases are completed in just 2 movements or strokes of the piston. This means there's a power-producing event with every single revolution of the crankshaft, generally giving them a higher power output for their weight. However, older two-stroke designs weren't very fuel efficient and produced more emissions, which limited their use in aviation. Modern two-stroke designs, especially those using compression ignition, are becoming more viable, with improvements in areas like lubrication and direct fuel injection.
And the four-stroke cycle, which I believe is much more common in general aviation aircraft today.
That's right. The four-stroke engine completes the intake, compression power, and exhaust processes in 4 separate strokes of the piston. So let's break down those 4 strokes. First, the intake stroke. The piston moves down, an intake valve opens, and the fuel-air mixture is drawn into the cylinder. Second is the compression stroke. The intake valve closes, the piston moves up, squeezing that mixture into a smaller space. This compression is really important for getting more power when it ignites. Third, the power stroke, the compressed mixture is ignited, creating a rapid expansion of gases, and a huge pressure increase that forces the piston back down, which in turn rotates the crankshaft. Finally, the exhaust stroke, an exhaust valve opens. The piston moves back up, pushing the burned gases out of the cylinder.
So 4 distinct movements to complete one cycle in each cylinder. And in an engine with multiple cylinders, each cylinder is doing a different stroke at any given moment, all working together to provide that continuous rotational power to the propeller shaft.
Exactly.
It's almost mind-boggling to think about that precise sequence happening so many times a minute.
It is. It's a beautifully synchronized process. And as you said, it relies on all those supporting systems. The fuel delivery, the ignition if it's a spark ignition engine, the oil for lubrication, the cooling to prevent overheating, and the exhaust to get rid of the waste gases, all working perfectly together.
Fascinating stuff. The last classification mentioned is the method of cooling. Liquid versus air. That seems pretty straightforward. But are there any important differences we should know about in the context of aircraft engines?
You're right. The basic idea is simple. Some engines use a liquid coolant, similar to what you find in a car, to carry heat away from the cylinders, while others rely on the air flowing over specially shaped fins on the engine to dissipate heat. Horizontally opposed engines, for example, are most commonly air-cooled. The choice of cooling method often depends on the engine's design, its power output, and the type of aircraft it's intended for. Each method has its own set of advantages and disadvantages when it comes to weight complexity, and how effectively it can cool the engine under different operating conditions.
Okay, so we've seen the evolution of these various reciprocating engine designs. Now let's talk about a more recent development in this area, the increasing role of diesel technology in the world of aviation. I know it's been a staple in cars for a long time, but it seems like its application in airplanes is a more recent development.
It has definitely gained momentum in recent years. As you mentioned, Frank Thielert really spearheaded this in the mid-1960s, taking inspiration from automotive diesel engines. The big advantage here is the similarity between diesel fuel and kerosene,
Right.
which means these engines can run on standard aviation jet fuel. This offers more independence when it comes to fuel availability at different airports, can lead to greater reliability, and often results in better fuel economy and lower overall operating costs.
Because it's primarily about fuel efficiency and potentially lower costs. Who are some of the key players in actually bringing certified diesel engines to general aviation aircraft?
Thielert Aircraft Engines, which was formed in 1999, produced the first certified diesel engine for general aviation after World War II back in 2001. They really paved the way for this technology in modern aircraft. Since then, other manufacturers like SMA have also started producing jet-fueled piston engines. You can now find these engines in aircraft like the Diamond DA-40 and DA-42, and they're even being offered as retrofits for popular aircraft like the Cessna 172 and Piper PA-28.
And these modern aviation diesel engines, are they pretty sophisticated in terms of how they're controlled?
Absolutely. Full Authority Digital Engine Control, or FADEC, is typically standard on these aircraft. This means the computer is constantly tweaking things like fuel flow and ignition timing to give you the best possible performance and efficiency without you having to manually manage those complex settings.
That's a nice lead-in to our next main area, the propeller, because all the power that the engine generates needs to be effectively translated into making the aircraft move forward.
Exactly. The propeller is essentially a rotating airfoil. Very much like the wing of the aircraft, it's subject to all the same aerodynamic principles, including induced drag and the potential for the blade to stall if the angle of attack becomes too high. Just as a wing generates lift, the propeller generates thrust, which is what propels the aircraft forward. The amount of thrust it produces depends on several factors: the specific shape of the propeller blade, its angle of attack, which is the angle at which the blade meets the oncoming air, and the engine's revolutions per minute, or RPM.
I've noticed that propeller blades often appear to be twisted along their length. Is there a specific aerodynamic reason for that design?
Yes, that twist is absolutely crucial for creating uniform lift, and therefore thrust along the entire length of the blade. Think about it. The very tip of the propeller blade travels a much greater distance in each rotation than the part of the blade closer to the hub, meaning the tip is moving much faster. To compensate for this difference in speed, the blade is designed with the highest pitch or greatest angle of incidence at the hub and the lowest pitch at the tip. The key insight here is that this isn't just a random shape. It's specifically designed to ensure every part of the blade is working efficiently to generate thrust, even though the tips are moving much faster than the base. Without this twist, the inner part of the blade could end up with a negative angle of attack at higher airspeeds, actually producing drag, while the tip could stall, losing its ability to generate effective thrust.
That makes perfect sense. Now, for smaller aircraft, the outline mentions two main types of propellers: fixed pitch and adjustable pitch. Let's start with fixed pitch. What are the key characteristics of these?
A fixed-pitch propeller has blades with a non-adjustable angle. It's set by the manufacturer during its construction. This means it's designed to be most efficient at a specific combination of airspeed and engine RPM. Because of this fixed setting, it's always a compromise. It won't be perfectly optimized for both taking off and climbing, as well as for cruising at altitude. However, fixed-pitch propellers are simpler in design, lighter in weight, and less expensive to manufacture and maintain. So they're often used when these factors are important considerations.
And within fixed-pitch propellers, we have climb propellers and cruise propellers. What's the fundamental difference in their design, and how does that affect performance in different phases of flight?
Exactly. A climb propeller is designed with a lower blade pitch, which means the blades take a smaller bite of air with each rotation, creating less drag. This allows the engine to spin faster, achieving higher RPM and thus more horsepower during critical phases like takeoff and climb, resulting in better performance. However, the trade-off is that it's less efficient at higher airspeeds during cruise. A cruise propeller, on the other hand, has a higher blade pitch, taking a bigger bite of air. This leads to lower RPM and horsepower during takeoff and climb, but it improves efficiency and fuel economy when you're cruising at your desired altitude.
So it's about prioritizing either getting airborne quickly or maximizing efficiency once you're at cruising altitude.
Exactly.
Now, how is the propeller typically connected to the engine in a fixed-pitch system?
Usually in a fixed-pitch setup, the propeller is mounted directly onto the engine's crankshaft. This means that the propeller RPM is the same as the crankshaft RPM. However, it's worth noting that some engines utilize geared shafts, which can result in the propeller spinning at a different rotational speed than the crankshaft.
And how do we as pilots flying an aircraft with a fixed-pitch propeller monitor the engine's power output? What instruments do we rely on?
In a fixed-pitch propeller aircraft, the tachometer is your primary instrument for indicating engine power. It's calibrated in hundreds of RPM, giving you a direct reading of how fast the engine, and therefore the propeller, are spinning. The tachometer typically has a green arc that indicates the normal continuous operating RPM range, and there may be other color-coded markings that signify specific limitations. It's crucial to always refer to the aircraft's Pilot Operating Handbook, or POH, or the engine manufacturer's recommendations to understand these markings. You control the RPM and consequently the power output, using the throttle which regulates the flow of the fuel-air mixture to the engine. Generally speaking, at a given altitude, a higher RPM reading will correspond to a higher power output from the engine.
But the number on the tachometer is the complete picture of power output, right? Power is always directly tied to the RPM shown.
Not entirely. While RPM is a very good indicator, it's important to remember that at higher altitudes, where the air density is significantly lower, the same RPM will actually produce less horsepower compared to operating at sea level. This is because the engine's power output is directly influenced by the mass of air it can take in. So as you climb and the air becomes less dense, you'll need to open the throttle further to try and maintain the same RPM. Therefore, the tachometer reading alone might not perfectly reflect the true power being developed at higher altitudes. Okay, that's a crucial point to keep in mind as we gain altitude. Let's move on to adjustable pitch propellers. The outline first mentions ground-adjustable types. How do those differ from the fixed-pitch propellers we've just discussed?
With a ground-adjustable propeller, you have the ability to manually change the angle of the propeller blades.
But this can only be done when the engine is not running and the aircraft is on the ground. This provides more flexibility than a fixed-pitch propeller, because you can set the blade pitch to be more optimized for a particular type of flying you plan to do. For instance, setting it to a lower pitch for better takeoff performance on a short runway, or to a higher pitch if you're primarily going to be cruising at altitude for maximum efficiency. Early versions of these might have had just 2 or 3 discrete settings like a low and a high pitch. But most modern ground-adjustable propellers offer a range of possible pitch settings. However, once you take off, the blade angle remains fixed at whatever setting you selected before departure.
So it's a step up in flexibility from fixed pitch, allowing for some pre-flight optimization, but it still requires a compromise because you can't change it once you're airborne. That leads us to the next type, constant speed propellers. These sound like they offer the most in-flight control and adaptability.
They definitely do. A constant speed propeller takes adjustability to the next level by automatically changing the blade pitch in flight. This is accomplished through a sophisticated component called a governor, which continuously works to maintain a specific engine RPM that the pilot selects. Regardless of changes in the aircraft's airspeed or the load on the propeller, it's the most common type of adjustable pitch propeller found on more advanced general aviation aircraft and offers significant efficiency advantages because it allows the engine to run at its most efficient RPM for whatever you're doing, and the propeller automatically adjusts to make that happen.
So with a constant speed propeller system, we now have 2 primary controls related to the engine and propeller, the throttle lever and the propeller control lever.
That's right.
How do these 2 controls work together to manage power and RPM?
The throttle still performs its fundamental job of controlling the engine's power output by regulating the amount of fuel-air mixture that flows to the engine. But now you also have a separate propeller control, typically a blue lever in most aircraft, which allows you to select the desired engine RPM. This selected RPM is still indicated on the tachometer. Once you've set a specific RPM with the propeller control, the governor takes over and automatically adjusts the propeller blade angle to maintain that exact RPM.
Could you give us a practical example of how this automatic adjustment of blade angle works during a typical flight?
Sure. Let's say you've set a cruising RPM. If your airspeed starts to increase, or if there's a decrease in the aerodynamic load on the propeller for some other reason, the governor will automatically increase the propeller blade angle, making it take a larger bite of the air. This increased resistance helps to keep the engine RPM from increasing above your selected setting. Conversely, if your airspeed decreases, or if there's an increase in the load on the propeller, the governor will decrease the blade angle, allowing the propeller to spin more easily and preventing the RPM from dropping below your selected value.
It's a really clever system, constantly making these tiny adjustments to keep the engine running at the desired speed. Now, the outline mentions something called the constant speed range. What exactly does that term refer to in the operation of these propellers?
The constant speed range refers to the range of possible angles that the propeller blades can adopt between their lowest and highest physical pitch stops. As long as the governor has room to adjust the blade angle within this range, it can effectively maintain the RPM that you've selected with the propeller control. However, if the blades reach either their lowest possible angle, the low pitch stop, or their highest possible angle, the high pitch stop, the governor can no longer adjust the pitch. When this happens, the propeller will start to behave more like a fixed pitch propeller. The RPM will then begin to vary with changes in the aircraft's airspeed and the load on the propeller.
That makes sense. The governor has a finite range of adjustment. Now, we also have a manifold pressure gauge in aircraft equipped with constant speed propellers. What information does that give us about the engine's operation?
On aircraft with constant speed propellers, the manifold pressure gauge is a primary indicator of the engine's power output. It directly measures the absolute pressure of the fuel-air mixture inside the engine's intake manifold. That's why it's often referred to as manifold absolute pressure, or MAP. At a constant engine RPM and altitude, the amount of power the engine is producing is directly related to the density of the fuel-air mixture that's being drawn into the cylinders. When you increase the throttle setting, more fuel and air are allowed to flow to the engine, and this results in an increase in the manifold pressure reading.
And what would the manifold pressure gauge typically show when the engine isn't running, or if there's a significant engine problem in flight?
When the engine is not running, the manifold pressure gauge will essentially display the current ambient atmospheric pressure. When you start the engine and it begins to draw in air, the MAP reading will drop to a value that is lower than the ambient pressure.
Interestingly, if you were to experience a significant engine failure or a substantial loss of power in flight, the manifold pressure would actually increase, moving closer to the ambient air pressure at your current altitude.
The manifold pressure gauge, like the tachometer, also have those color-coded arcs, right? What do those signify?
Yes, just like the tachometer. The manifold pressure gauge typically has a green arc that indicates the normal range of operating pressures, and a red radial line that marks the upper limit of allowable manifold pressure. It is absolutely crucial to operate the engine within these marked limits, to avoid putting excessive stress on the engine's internal components and potentially causing damage.
And what's the proper technique for adjusting the power settings when you have a constant speed propeller to prevent overstressing the engine? Are there specific rules we need to follow when using the throttle and propeller controls together?
Yes, there is a specific sequence you should adhere to when changing power settings to prevent creating excessive pressure within the engine cylinders. When you're decreasing power, the general rule is to always reduce the manifold pressure before you decrease the engine RPM using the propeller control. If you reduce the RPM first, the governor might automatically increase the blade pitch, which in turn can cause the manifold pressure to rise, potentially exceeding the engine manufacturer's limits. Conversely, when you are increasing power, you should generally increase the engine RPM using the propeller control before you increase the manifold pressure with the throttle. Also, it's generally advisable to minimize the amount of time you operate the engine at maximum RPM and maximum manifold pressure. You should also specifically avoid operating at maximum RPM with a very low manifold pressure, especially in radial engines. Always refer to the specific recommendations provided in your aircraft's Pilot Operating Handbook, or POH, or the engine manufacturer's documentation for the correct power setting procedures for your particular aircraft.
Those are some really important guidelines to remember when flying with a constant speed propeller. Finally, the outline mentions a specific FAA Special Airworthiness Information Bulletin, or SAID, that had to do with propeller overspeed in aircraft with variable pitch propellers. What was the main concern highlighted in that bulletin?
That SAIB from 2010 brought attention to the potential for an unexpected increase in thrust in certain unusual situations, particularly in scenarios where the propeller blades might be at their lowest possible pitch setting. The bulletin discussed how in some specific aircraft models, if the airspeed were to drop below the best glide speed, the speed that gives you the greatest distance for altitude lost in an unpowered glide, the increased thrust produced by the propeller in its low pitch setting could actually allow the pilot to maintain level flight rather than descending. The concern raised was that in such a situation, the best glide speed might not always provide sufficient thrust for safe flight, due to the complex interaction of various factors related to the specific aircraft design, the engine characteristics, and the propeller's performance. It serves as an important reminder that having a thorough understanding of your specific aircraft and all of its systems is absolutely paramount for safe operation.
So there you have it, a foundational look at the engine and propeller systems that are so vital to how an aircraft operates. We've covered a lot of ground.